So in class today we looked at cotangent, tangent, secant, and cosecant graphs, and we talked about the parent functions of those and how we get them. Now we're going to look at how you would figure out what a transformation is that's occurred in one of those graphs. So I want to make sure it's still recording because I don't know where the little thing just went. There it is. Here, even though it's a little bit hard to see, but it does keep going up forever, we're looking at a cotangent graph. If you look back at the parent graph we did in class, cotangent was the one that kind of had the negative slope to it. When you're looking for what's happened with the cotangent graph, you want to find the middle of the graph. You always have these groups of 3 points that are happening in each one of our cotangent periods. And if you look, it's kind of divided into 4 sections. We have exactly halfway in between our period, and in this case, the period of this cotangent graph goes from pi over 4 to 9 pi over 4. So the period of this happens to be 2 pi. As we learned when we did our parent functions, the period of a cotangent graph is typically pi. And so the way you would find b is to say that pi over b is equal to our period. So the first thing we'll do is we'll actually solve for b, and I want to make this pen a little bit skinnier. We'll solve for b and say that 2 pi equals pi over b. And so we're going to get that 2 pi b equals pi, and b is equal to 1/2. So we have our first variable. Now, as you're looking at all of these groups of 3 points, you're again going to draw a midline down your graph. This midline is how you're going to get your k. How far up from the x-axis did this shift? Well, we have a line at y equals 5, which makes k equal to 5. So we have our k and we have our b. Now, when we look at the shift that's happened from our parent function, if cotangent is cosine over sine, then anywhere where sine would equal 0 would be where an asymptote is. So sine of 0 would be 0, where our first asymptote is at pi over 4. So we can say that this has shifted to the right 4 units, so our h is actually pi over 4. Now when we plug it into our equation, it's going to give us x minus pi over 4. And now let's look at what's happened to a. In these 3 distinct points in our parent function, when we're going, 1/4 of the way over, if a were just 1, then it would just change by 1. But if we look, then the y values would just change by 1. But when we look at what's happening here, we actually have that from this point to this point, our y values changed by 3. And so this one has been stretched vertically by a scale factor of 3. So we're going to say that a equals 3. So our final equation for this one is going to be 3 times the cotangent of b times x minus h plus k. And that's it. You only need to come up with one equation. I could ask you to come up with a tangent, but let's not. So the next one, we're looking at this saying, well, okay, I know that this is either going to be secant or it's going to be cosecant. One of the easiest ways to see what this function is going to be to draw the sine or cosine curve that would go in with this. And remember, this is always hitting, if we draw in the sine or the cosine function, the cosecant or secant function is always hitting at the maximum and minimum points. Because whatever A, B, K, and H are for that sine or cosine function, that's exactly what it's going to be for our secant or cosecant function. So I'm just realizing I did a bad thing on this graph. When I drew it, I made a slight mistake, and that's right here. It's not consistent all the way. So let me get that fixed real quick. This one should go all the way down to 4, and then this sine function will look a little bit more normal. So the next thing we want to do is we want to draw in our midline of the function. And our midline is going right through here. This is going to allow us to see the amplitude of the function and apply it to whatever it is. Now, if we look at what's happening with this red graph, I think the easiest thing to see is that we have a period of sine beginning right here. And it's nice to pick sine in this case, one, because it looks a lot like our parent function. It goes frowny face to happy face, and there's no phase shift in it. So that's a good one to start off with. Now, if we're relating it to sine, what's related to sine? Cosecant. So in just looking at the sine function, we see that it's shifted down 2, so k is equal to -2. Let's look at the period that this of this cosecant function, because that's what we're going to be finding. And the period goes from 0 to pi. That's where we get both of our parabolas in there. Now, for a regular cosecant function, we have that 2 pi over b is equal to our period. Well, in this case, our period is equal to pi, so b is going to be equal to 2. Now the next thing we're going to look at is our a, and our a is going to be exactly the same as it would be for our sine function. If we look at the amplitude of the sine function related to this cosecant function, it's 2. And then our phase shift in this happens to be 0. We haven't shifted it at all. So our final function for this is going to be y equals 2 times cosecant of 2x minus 2. And you can go ahead and put that in your graphing calculator and see if this is what you get. It should look almost exactly the same if you do a window with an x minimum of -2 pi and an x max of +2 pi, and then do your x scale by pi over 4. That would be a great way to look at these in your graphing calculator. So I hope that helps. Just do those 7 graphs. Don't worry about graphing the 3 equations that are on that sheet. Just find one equation for each of the 7 graphs. Thank you.